Today we're going to look at two things. One is called the side Angleside area formula, and the other one is called the law of sines. We need the area formula in order to prove the law of sines, and both we will prove today, and we will use the law of sines a little bit today as well. So let's look at one problem with the law of cosines here. So here's my basic formula. Remember that the important part about this is that these are the two sides, and this side is opposite this angle, okay? So I do have an angle, and I have a side opposite, so maybe I'll call my F the C, okay? Which is what I'm looking for anyways. I'm looking for F. So here's the situation. The campers measured the distance from a flag to this house. They measured the angle for a line of sight to the boathouse over here. And they know this angle from the flag to the boathouse as well. So the question, of course, is, can we find out what F is there? So in starting to plug things in, I'm going to call F my C, so that's F squared. A has to be one of the sides, so let's call that the 400 squared. Unfortunately, I don't have that other one. So now I put the 400 in, I put my H there, I do have my cosine of 40 degrees. Excellent, except not. The problem now is that I have an F and an H. Two variables require two equations. So the breakdown here is that we have too many variables, okay? Now, somebody originally said, holy, learn to spell, Captain. Somebody else said up there, oh, it's not side, angle, side, or side, side, side. Great, that's the reason, but this is the reason why we can't do that. Because if we don't have this scenario, we have too many variables. Okay, so there we see the limitation of the law of cosines. So today we're going to introduce something called the law of sines, which will help us in a situation, for example, in this situation, which is angle, side, angle. Before I can look at what's called the law of sines, we're going to derive something called the side angle side area formula for a triangle. So let's take a gander over here. Using trigonometry, we're going to come up with a formula that can find the area for any triangle. Now, we already know that if I just have this triangle, notice triangle ABC is the large triangle there. And your area, in this case, just to not confuse it with angle A, I'm calling it area is K. So the area K is equal to 1/2 base times height. Remember, base and height are always perpendicular. So it never matters what you call the base. This AB could be the base. You just have to call the height over here. Or this could be the base. I just have to call the height over there. So the base and height are always perpendicular. In this diagram, here's base and here's height. Well, if you don't have H, you now have a problem, because I can find out base pretty quick. I might have B because it's the side of the triangle. So the question is, how do I find height right there? Well, if H is not known, you can use H to find, you can find H using this triangle right here, which is triangle BCD. So, using that triangle, if I know this angle, this is opposite, and this is hypotenuse. So, relative to angle C, opposite over hypotenuse is H over A. And if I want to get H by itself, I just multiply both sides by A. So now what? Well, if I were to substitute this H, A times the sine of C, into there, we get this. So K is 1/2 B times A times the sine of C. And now let me just clean it up a little bit. So the area of the triangle is 1/2 AB sine of C. So in any triangle, if you know two sides and the included angle, then this formula right here will always work. Again, it doesn't matter what you call AB, just as long as this angle is the angle in between, okay? So in any triangle, the area is 1/2 the product length of any two sides and the sine of the included angle. Hence, side angle side. Hence, side angle side. All right, so now let's get into something called the law of sines. Some people like this law of sines better than the law of cosines because look at this one. Look at how the law of sines are. The sine of the angle A is over the side A, so these are opposites, equals the sine of B over the B, equals sine of C over C. So essentially, it's just an extended proportion. So people like that one better because it is significantly less complicated looking than something like this, which you don't need to write. And again, if we have, a few of the parts here, I can set it up and I don't have to use this fraction. I can just solve this proportion or solve this proportion or solve this proportion. So the law of sine, the setup is a lot more, people say, logical, or at least it looks cleaner. And it helps us where the law of cosines does not. So let's see where that comes from. So triangle ABC is any triangle, obtuse, right, or acute. So to find the area of triangle ABC, here's what we can do. We already know, we just did it, that it's 1/2 AB times the cosine of C. Since area does not change, if I had a different perspective and I use BC instead of AB, this has to be the cosine of A. And what's my mistake? I already made a mistake here.
You wrote cosine.
I wrote cosine, yeah. Okay, so there we go, and there. All right, and so let's repeat that process. 1/2. This time I'm using AC, sine of B. Again, notice the pattern here. AB is here, capital C is over there because that's the included angle. BC here, capital A is over there, AC, capital B there. So let's start cleaning things up. If you multiply everything by 2, you get this. Multiply by 2 here. And AC times the sine of B. And then here we times 2 all across the board. And now, if you divide by ABC everywhere, divide by ABC, and when I say ABC, I mean these are the side lengths, A times B times C, as opposed to the angle measures. Notice what cancels out. A and the B and the B. Here the BC drops out, and here the AC drops out. So what are we left with? The sine of C over C, the sine of A over small a, and the sine of B over small b. And we end up with quite an elegant looking extended proportion. So here's the lake situation from the warm-up. And we're going to find the distance across the lake. So if you couldn't tell, this whole little thingamajigger is the lake. And this is just the line of sight from a house to a houseboat, or a boathouse over here. And here's a flag line of sight. So they're able to measure this degree and this degree. But these two going on the water, so they were unable to measure those. So we're trying to find out what F is here. Well, notice the pattern we have. Here's an angle, here's a side, and here's an angle. And let's pay attention to what is opposite. The 40 degrees is opposite side F. So whatever we call, if I did sine of 40 degrees, then that's going to be opposite the F right there. So we have to place that as the ratio. Next, I'm going to start filling in some more. So here is B, which is opposite the 400. So sine of B is opposite the 400. And our last situation is the sine of 110 is opposite the H. Now, what's the problem here? Consider this. As we see, the problem relates here is that I have too many variables. I don't have a proportion that I can set up that'll actually give me just one variable. So, using the triangle sum theorem, or sometimes called the triangle angle sum theorem, we know that in a triangle, all three angles sum to 180. So that means this here together is 150, so this angle B has to measure 30 degrees, which means I can actually replace that right here with 30 degrees. And notice the proportion I can use here. The sine of 40 over F is equal to the sine of 30 over 400. Now, however we want to isolate, we can cross multiply, but remember the shortcut for getting F by itself here is you multiply diagonally and you divide horizontally or vertically. So here's what I say. You can multiply these two together and divide by the sine of 30, or multiply these together and divide by the sine of 30. So always multiply diagonally, and you're going to divide horizontally or vertically. So let me just jump to that result. 400 times the sine of 40 degrees divided by the sine of 30. As a reminder, the sines do not cancel out here because sine of 40 is a number, sine of 30 is a number. Just like if I had a plus and a plus, for example, 3 plus 2 and 5 plus 7, I wouldn't cancel out the pluses because those are operations. In the same way, I don't cancel out the 40s there, or excuse me, the sines there. So we just plug all that into our calculator to see what we get. So when we finally plug and play into our calculator, we get approximately 514.2 meters. Of course, 514 is an acceptable answer on that one. All right, please attack, kill, destroy. It might be wise for you to start by drawing a diagram. I do want to walk through what south of east means. 17 degrees south of east. So if this is east going right here, then 17 degrees is like that. Kind of like angle of depression. Just says, so here's my east. I'm going 17 degrees south of east. South means I'm in the downward direction as opposed to 17 degrees north of east, which would be up here. All right, so let's read through this and draw the appropriate. Folks, you won't get the diagram right the first time, so expect mistakes and do not give up. So from Bud's house, which I put low, but at first I put high when I was drawing this, and I realized I had to change it because Bud's house is north. So, or excuse me, Pal's house. Bud's house is, from Bud's house, a tower is 17 degrees south of east. So this direction is east, so that's the blue line, and 17 degrees is just that little angle right there. So I drew from here, I drew this, what now became an obtuse angle. All right, from Pal's house, which is 4 kilometers due north, so there's my straight up due north, it is 40 degrees south of east. So because of that, this is 40, complement is 50 inside there. So how far is it from Bud's house to the tower? So we're trying to find Bud's to the tower. So let's look at the diagram a little more closely here. I didn't know where this line was. Notice that I have extra drawing here. What I did was measure the 40 degrees, and clearly this is too big. This should not be that big. It should be closer to here. I just kept drawing that line this way. And then from 17 degrees south of east here, I just kept drawing that line. And where the two intersected, that's where the tower is. Angle, side, angle, effectively is what we're doing here. So the question is, we're trying to find out how far it is from Bud's house to the tower. So for the sake of the diagram, I'm going to call this P. But you could call it D or whatever. Why did I call it P? Because it's opposite that angle from Pal's house. Again, you can You can label it however you would like. All right, now I'm looking for this angle. And remember, the key is, excuse me, I know this angle. I'm looking for the side. The key is that whatever I set up, I need to have a pair of opposite side and angle together. I need a ratio. The ratio is the key. It's kind of like my scale factor. Okay? So I need that something opposite. So here's my side, PB is 4. So the angle opposite, I do have to find out what that is. So again, triangle sum theorem says all three angles are going to add up to 180. So this is 157. So that means this one is going to be 23 degrees. So now I have a 23 degrees and my 4 kilometers. So the sine of 23 degrees is over the 4. And this next one is, since I'm finding this P here, I'm going to go opposite this angle measure P there. So sine of 50 degrees is over the length P. And now getting P by itself, remember we multiply diagonally and we're going to divide horizontally or vertically. So 4 times the sine of 50 divided by the sine of 23. All that can go into your calculator. Remember, before we even know if this is 4 and my drawing is roughly scale, P actually does not look too far from 4, except for the fact that I know that this is too big and this one's too small. So my guess is P will be larger because if this is the smallest angle, this one is the middle angle, so it's got to be bigger than 4. So my diagram is not to scale. It looks like it would be 4, but my guess is it's actually closer to 6, 7, or 8. And when I solve, I get 7.8 kilometers, approximately.